Thanks. Okay, I'll get cracking. So Ben's done a lot of really good introduction work, which I deleted from my slides craftily while he was talking. So I'm going to talk to you today about some of the multiphysics work we're doing to improve support for fusion component design. Not to denigrate Ben, but the plasma part, we basically hot gas and keep it hot. And that's fusion done. That's all we have to do. Yes, there are complex phenomena, interactions between the various parts of the plasma. We model that, but fundamentally, from the large scale of things, it's a hot gas in a box. And today I'm going to talk to you about the box. The main components are some large toroidal field coils which sit around the tokamak, the colloidal field coils. The combination of both gives you stability and control. The PF coils, these ones here, for example, are used to shape the plasma. Just to give you an example of what one would look like, issue my internet connection is going to behave today very good. So this is from an old UKA tokamak which was gifted to the Prague Institute of Plasma Physics. The bits that glow the brightest are the coolest. These are usually where the plasma is in contact with the wall, but you can see some of these nice bits of, I presume, bits of floating metal, crap that's come off the wall, which bremsed along a lot and glows really, really brightly. But the key thing here is that to note that the brightest parts are actually the coolest. The bits that you can't see actually are radiating the most and the most power, and that power is all going to go somewhere. Ultimately, in a tokamak-like mast, which is a very open configuration, you have colloidal field coils inside the tokamak. You have toroidal field coils outside of it, and the central solenoid down the middle. And any stuff that does escape is going to impinge on these various bits and pieces of wall. Otherwise, the other major engineering component we have is the diverter, which is this big chunk of material, usually at the top or bottom. It can be both in this case. This is known as a double null configuration. And these components are designed to deal with extremely high heat loads. This is a side note, this particular design of diverter is called a Super X diverter. And this allows a large expansion of the magnetic flux lines down here, which allows the incoming heat flux to be distributed over a much larger area, which would otherwise be concentrated into a much smaller area, which makes the design of components challenging / impossible. But in terms of what is going on, the energy from the plasma mostly comes out in the form of neutrons. These neutrons, despite having a small magnetic moment, do not feel a magnetic field and largely go uninhibited straight into structure materials, where they deposit their heat over a relatively large volume. That power, ultimately, we want to do something useful with. Unfortunately, because of that savage Carnot, we lose an awful lot of the energy we do just in lost efficiency. And ultimately, for this fusion power of 2400 megawatts, we end up with 625 megawatts. So really, what we're worrying about here is all this power that's produced that is not going towards electricity has got to go somewhere. And that's largely what we're going to worry about here. We have lots of energy stored in the magnets. In the case of these are the eta toroidal field coil magnets. You're seeing the large structure for them. They have total current in them, upwards of 70 megaamps, forces upwards of half a giganewton. There's an awful lot of crosstalk between the coils. The coils themselves, they are superconducting, so they are cooled to about minus 260 something Celsius to liquid helium temperature, where they are superconducting. They are quite complex in shape. And just as a side note, took the entire world's superconductor production for something like 8 years to produce them all. At the first wall, somewhere in the middle, where the bright bit is, your plasma-facing components can be at temperatures upwards of 4,000 Kelvin. So I'm not sure if Ben mentioned it, but the core of the plasma can be upwards of 150 million Celsius. You get to the first wall where it's about 4,000 Kelvin in certain parts, and then to the superconducting coils, which are then 4 Kelvin. So a large part of our material problems are driven by stress and strain from thermal expansion. Radiation damage, of course, induces an extra source term in terms of stress. And particularly for magnets, rapid heat transients in very cold things can be a problem, also known as a magnet quench. This is where the superconducting coils lose their superconductivity very quickly and become incredibly resistive very quickly, where you get a large amount of energy. All that stored energy becomes released as heat. This happens so quickly, we have to rely upon a different heat model, the non-Fourier hyperbolic heat model. Further, we have blankets or liquid metal diverters, if we're feeling really fancy. This leads to problems we have to worry about with MHD. So we have these fairly large, relatively slowly flowing liquid metal concepts, but that's not the only concept. There are other liquid metal concepts we can consider. And certainly one of the more preferable diverter concepts would be a liquid jet of liquid metal. That would be a very nice kind of diverter. Of course, you have to worry about turbulence in terms of fluids. So we have, in some concepts, gas coolant. We have, in some cases, water coolant. In other cases, we have combinations of CO2, helium, liquid metal. And some of these can be quite turbulent flows sometimes. And certainly in the case of some of the more detailed components, we have to worry about fluid structure interaction inside some of these components. Further, in terms of heat sources, the plasma, of course, releases heat in the form of charged particles and radiation. Charged particles leaking from the edge of the plasma. We have neutrals, which can be fast neutrals, can impinge on the wall. We're going to have neutrons, X-rays, gamma rays. This tends to be distributed over a large area, or it can be very concentrated. So in the case of the charged particle heat from the plasma of the diverter, we're talking between 5 and 20 megawatts for survivable scenarios. But there are a certain number of off-normal scenarios, for example, runaway electrons, which can cause tremendous amounts of energy to be deposited. The electrons end up getting accelerated to energies of about 20 MeV and slow down very quickly when they hit a tungsten wall, but there's also a lot of X-rays produced, which is an awful lot of energy being deposited in one space. The neutrons, as I mentioned earlier, the neutrons carry the bulk of the energy from fusion, so 80% of it. This is really quite important because not only are they the source of many of our problems, they also are used to breed the tritium fuel we actually need. So a combination of the radiation damage increases the stress and strain. We also have nuclear heating, which is a source of thermal expansion. And further complications with the neutron interactions can increase that energy deposition from neutrons by a further 50%. And of course, one of the things that's often forgotten about is infrared radiation in the case of emission from a hot surface on the inboard, say, to the outboard. In terms of vacuum, we have other problems. So as Ben mentioned, and from the case of Irene, we can look at the follow the particles explicitly in this case because the vacuum is so good into molecular species model, essentially ray tracing, to work out how good our pumping efficiencies are. We also have to worry about tritium permeation. So although tritium will be released from the plasma sometimes and get stuck to the walls, it will also be produced in the blankets. And really, if we want to be good at predicting how much tritium is produced from a particular design, we need to get good at actually following the tritium where it goes, when it gets stuck into coolant flows, when it gets embedded in materials, and how it comes out. Further, we have other material problems, so erosion. We have these interesting tungsten fuzz problems where charged particles can, when they impinge on the wall and diverter structures, can produce this tungsten fuzz, which leads to these very nice fingers of tungsten being produced, which is really pretty and interesting. But what this means is you have these gaps in between the tungsten, so the heat transfer coefficient is terrible horizontally, but along the fuzz is quite good. But this overall leads to a drop in heat transfer, and because that drop in heat transfer happens, it actually makes the tungsten fuzz worse. So looking from, if we want to model the response of the tokamak to the plasma in its entirety, we firmly have a multi-scale problem, going from the atomic level, where neutron interactions can cause interstitials and defects, which then will go up to larger models to see how that impacts in a particular grain, up to the point where how that grain moves around and how that grain impacts the macroscopic phenomena. And as Ben mentioned very kindly, of course, the plasma itself, we also have a number of different timescales to worry about, both length and time. So we have a temporal problem as well as a scale problem. A further problem is the traditional set of tools that we use are often used beyond their validation case, whether people realize it or not. Especially if you want to consider the engineering response of the tokamak, many of these tools are used when we have multiple loads, multi-component loads, and they have not undergone the appropriate validation that would be required from a safety relevant code. And we need to use uncertainty quantification to help breach these gaps. So in terms of timelines in between now and 2040, so I'm not sure if any of you heard, but we've been running this design study for a tokamak called the STEP project, which is to take a critical look as to whether we can actually build a spherical tokamak. The idea is by the end of 2024, we will have completed tranche 1, which is to have a concept design. There'll then be a further 2 tranches, tranche 2, where we go into detailed design and construction, and then finally the construction phase starting in around 2032 to be running by 2040. The current plans are for a spherical tokamak-based power plant, and there are a number of siting questions currently ongoing as to where we'd place such a thing. This is a very ambitious timescale. I should note that if I draw on some important lines here, the dashed grey line is the first ETA plasma, the first just full stop first ETA plasma. This is the first DD plasma, I think, and sometime around 2038 we can expect our first DT plasma. So in terms of getting some validation from another tokamak that we can easily get access to is going to be a challenge. Of course, coming online soon, maybe Spark in the next few years, in the next 5 years or so. We'll have access to IFMIF, which is another nuclear test facility, but that's minus a lot of the magnetic loads. We have Chimera, which has the magnetic loads, but does not have the nuclear component. So in terms of getting these integrated tests, these integrated validation cases, we are, for want of a word, lacking. So we need to use much more intelligent techniques to be able to actually sample the uncertain space appropriately and get validation data where we can. So here's an example of a fusion neutron transport problem, a particular benchmark problem. So we have experiment. So the blue dots and the orange dots, they are experimental data points for a particular neutron spectrum for a particular case. And the red lines and the green lines are the range. The blue is the green is the average. The red is the range given by all the possible ranges of all the uncertainty of all the nuclear data. So accounting for all the uncertainty in all the nuclear data, there's still not enough range to cover some of the discrepancies between the experiment and the simulation. So we are also in one dreadfully in terms of neutron data. So traditionally, the tools that engineers use to design tokamaks are entirely manual and are built on humans and approximations. A human will take a look at a CAD model and will simplify it on the basis of their experience and knowledge. They'll then go off traditionally with a traditional mesh generator built into their analysis package, which is going to be tedious, it's slow, and it's not parallel. So immediately, that part of the problem takes a while. So it can take months to go from CAD geometry to running problem. And when you do get a running problem, these commercial solvers, which they tend to use, do not scale well beyond 32 cores. So to really make progress on how we can scale up the size of our engineering problems, we have to move the engineer off the desktop into something more scalable. Here's an example of a sub-modeling problem where they took a particular colloidal field coil, in this case I think it's P5 coil, which hangs off the mast upgrade vacuum vessel. And if we wanted to look at the dynamic response of the entire tokamak, that would be not possible with such a simple model. If we then also want to go into this more uncertain or data-rich space, if we combined what we could do with a really performant FEA, finite element analysis system, with image-based finite element analysis, so image-based finite element analysis allows you to use neutron or X-ray radiographs to image what components really look like using very, very high-resolution X-rays and neutron imaging. So, for example, this case here allows us to take what the component actually looks like, including all the defects, where there's been brazing failures, where the materials become separated from its joining locations. If you combine that kind of capability, so being able to do this kind of real FEA analysis, with something like this, which is digital image correlation, where you take a component, you cover it in this speckle paint. As that speckle moves around, you can determine what the real strain is. And that's what is being displayed on this color thing when this little paintball gun fires. If you combine this kind of experimental data, this kind of simulation data, we're heading towards a really good combination to allow us to go forwards to design stuff well. However, we already know that going towards as designed FEA is achievable. We took a ETA port plug, we meshed this using Gmesh. We wrote a special tool called PPPP, which takes our relatively, this is not a full detailed CAD model, but it's relatively detailed. The full component, meshed it on using Gmesh, pre-processed using our special tool, and in about 1.9 hours, you go from the CAD model to the mesh without having to do anything. And this is all parallelized. So we know for that we can end up with about 78 million elements. These are all just first order tets, so you can multiply that by factors of a few if you're going to go to second order tets, and then if we're going to represent that using a second order refinement in terms of the variables, we can end up with quite a large number of elements. But we already know from our colleagues at Cambridge that this is not unreasonable, and we should be heading towards this anyway. We already know from work done by Chris Richardson and Garth that in terms of getting scalable thermomechanical calculations, that is entirely possible. Ending up with the order of 10 to the 9 tets on 25,000 cores. This is not to be sniffed at. There is, of course, a role for machine learning and AI, and we have lots of problems that are ripe for the deployment of machine learning and AI, particularly in terms of simulation and parameter space exploration. Our main bottlenecks in terms of getting simulations going are mostly repairing and simplifying the CAD geometry. If you could really get machine learning and AI into that state, into that part of life, that would turn around our lives, I think. Mesh generation is another good place where I'd love to see the application of machine learning and AI. Same for transient fluid simulation and Monte Carlo radiation transport. Those two parts of our simulation workflows are particularly slow in comparison to the rest of the FEA. We do have a number of ongoing projects for physics-informed neural networks, and there's been some recent interest in Nvidia Simnet. If we combine everything we talked about, the ability to do large-scale FEA analysis and machine learning and AI, we head towards a world where we can really think about doing some physics-complete digital twins, where we can really show that we actually understand all the phenomena that are going on and predict that in comparison to real life. Here's an ongoing example from the University of Swansea, where they are going to use machine learning and AI to predict simulation results between experiments, so you don't have to do the simulations in between. And in the cases where that difference between prediction and experiment grows large, they would use more simulations to fill in the gaps. So if we do want to head towards a world where we're going to simulate full physics-complete systems, we need this large, scalable, called FEA framework. And it's got to cover many things. Computational solid mechanics, so including contact and fraction mechanics, computational chemistry, electromagnetics, fluid dynamics, radiation transport. The way I almost imagine it is if you imagine a fusion reactor or a bunch of stainless steel large Lego bricks, everything that could happen to that Lego brick we more or less care about. We do really, though, want to consider that it needs to be highly scalable, because we're going to have, if we head towards full reactors, that needs to be scalable. And we need to gaze at the exascale. We necessarily need more physics than most frameworks allow. But we do want to, be thinking about how we're going to move this across to the exascale when it arrives. So I think because we have this more holistic view of how we stick stuff together, we have lots of physics to stick in. We've been experimenting with tightly coupled frameworks rather than a federated model. And we do have a number of cases that warrant tight coupling. So, for example, this heat problem in superconducting magnets. Still figuring out what scales, what tools, what physics. But one of the key things we already know about is that the engineer will be limited by where they can deploy their software. So open source, open licensing is absolutely critical for anything that we do. We did some initial investigations. A chap who works with us called Alex Dubas looked at a range of different FEA packages, finite element libraries. We had to start somewhere. So we tried to start off scientifically by comparing against, performance and stuff like that. But ultimately, after going through comparing 37 different packages, we had to down select on how easy it was to use, how much documentation there is, software quality, and scaling is obviously important. Memory usage is important. We ended up looking at 3 different libraries: MFEM, Moose, and Dolphin. And in the end, because we have on the STEP program, we have to be application driven. We perhaps didn't take the most scalable solution. I went with Moose because it has much more physics that is ready to go and ready to scale. And for a number of other reasons, scale, multi-scale, other bits and pieces. That's not to say that we aren't going to consider other options in the future, but currently that's what we're using currently. So another argument for scalable FEA systems would be the Sleipner A disaster, which was caused by a blockage in terms of computational resources. Traditionally, people would use submodeling to solve one of the particular problems with this disaster, but they didn't. And if instead they had access to a much more scalable solution, this could have all been bypassed. So we've been looking at a bunch of problems. So in this case, this is a blanket pin concept of a breeding module. Here we're looking at the temperature and velocity induced in the cooling gas to see what happens as we ramp up this flow down the middle. And it turns out this particular the shape of this nozzle region is important. And we did an optimization study to look at a number of different setups. What we have found is
sorry, 3 minutes left over.
Okay, I think I'm nearly there. Obviously the parallel scaling is important, but what we have found immediately upon trialing out real problems, preconditioners, the physics and the preconditioning really limits scalability. So looking at when we couple in some really non-linear physics, which turns out is what most real problems are, it really hampers your scalability, especially when you've got make your problems all temperature dependent. We've been using Moose, which is based on libmesh, which then takes this FE assembly and sends it off to PETSI. And there is a GPU-enabled version of PETSI in progress. So the hope is that will be relatively easy to be able to hook into those benefits. We have found that for very tightly coupled problems, preconditioning is a challenge, but the field split preconditioning really helps here. Makes problems actually quite tractable. In terms of problems, as we go to bigger problem sizes, this is no different to anybody else in the exascale region. We need to rely upon in situ visualization, because transferring some of these huge meshes with tens of thousands of time steps, that really is not something that we can continue to do, shifting data back and forth, and geometry preparation. If we could do something about speeding that up, that would really make our life a lot easier. In terms of meshing, we've been using the Coreform trellis mesher. Basically, that's the starting point for compatibility with other tools. Gmesh we're getting better with, and now we can get in real geometry. That's really good. But the real one that I've been still blows my mind is a library called TetMesh, FTetWild, which allows it can mesh. Its tagline is we can mesh anything. So it took 10,000 things from the 3D printing library Thingiverse. And meshed them all successfully with something like 99.999% success rate. And the ones that failed just needed more memory. It was really quite incredible. They can just throw these triangle soups at it and it meshes. So I took one of my worst problems, and it failed, of course, but it's because the STL is not really valid. But it can do some really interesting things, really quite well. So, for example, you can take your STL input and put a background mesh around it to turn it into a fluid problem. However, going into this view of meshing, the real problem becomes boundary condition assignment. when you've got complex boundary conditions for contact or for heat transfer coefficients, it becomes a real pain. That being said, there are obviously some really interesting stuff coming down the academic pipeline. So isogeometrics is obviously super interesting because that allows you to increase our scale dramatically. Spectral HP-based finite element, again, super interesting. I think if the two were combined, that would give us a really nice framework for the future. But unfortunately, on the STEP program, we have to be pragmatic, and therefore we have to go with what's most capable now, and that which is why we went down the line of Moose. Everyone else is also thinking along these lines about scalability, so that makes it reassuring. Not going to cut to that too much. So this was possible 5 years ago to simulate a whole fission reactor core. We need to be able to take that and light a fire under that. So some examples, we've been doing calculations for stress strain calculations for digital image correlation to show that we get, first of all, get the same results as ANSYS, and that we also can show a more scalable result than they do. We've been doing problems for fluid flow in the arc reactor, reactor physics fluid flow problems, looking at hypervapotrons, a whole range of things. But the next real steps are to move on to fully couple this with a radiation transport. So what's next? We need to start thinking about how we can talk to the plasma physics, because of course the device does not exist in isolation to the plasma, nor the plasma to the device. So how we can couple those things together is going to be interesting. How we can bring this in together with the detailed blanket studies, because we have to really care about where tritium goes. And that's going to be a coupled temperature, mechanical, tritium radiation problem. And then ultimately heading towards large-scale digital twins of mass upgrade, hive, and heat. And that's all I'm going to say. So hopefully that was in time, and hopefully you have questions.